Hey guys, welcome back to the LearnAPCalc series here at LearnAP. In this video, we're going to talk about the second derivative test, concavity, and inflection points. So this is all sort of talking about things related to the second derivative of a function. We're going to talk about what is concavity, how to determine a function's concavity, finding inflection points, and using the second derivative test for relative extrema. As usual, guys, if you've got a question on anything in this video, you can ask in the comments, or you can also ask in our weekly live streams we do every Sunday from 4 to 5 p.m. Eastern. Other than that, let's get to it. Alright, so let's start by talking about concavity, and sort of what is concavity. Well, if I have a function, so I'll just draw this out, f of x, my concavity here is describing the rate of change of the first derivative. So it's the derivative of the first derivative, because remember, derivative is the rate of change of something. And like I said here, thus concavity is given by the second derivative of a function. Now note that our first derivative is written normally as dy dx. Our second derivative is written either, or this can also be written as f prime of x. This is written as d squared y dx squared. A lot of times you'll see it without the parentheses, but I think that this makes it sort of less ambiguous. And f double prime of x. So that's just a quick note about notation. Now a function that is concave down means that the rate of change of the first derivative is decreasing. So if you take a look back at this graph that I drew here, we can see that it's increasing. F prime of x is greater than 0. Now the rate at which I'm increasing is decreasing. So we'll say here to here, I'm increasing by, a fair amount. And if I have about the same distance, I can see that I'm in fact increasing less. So my rate of change of increasing is going down. So thus our second derivative is less than 0. And the second derivative describes concavity. If the second derivative is greater than 0, we're concave up. And if our second derivative is less than 0, we are concave down. And here's a good way of memorizing that. So here we have concave up, that's what concave up looks like, and here we have concave down. We can see that for concave up, we have these, it's positive, and here for concave down it's negative. So if you're ever sort of trying to think about it, just remember that up is happy and down is sad. But anyway, we also have another topic, and that is a point of inflection. So let's say that we go from concave up, happy, to sad. At some point here, we're switching from concave up to concave down. And that's what a point of inflection is it's simply on one side we are either concave up or concave down, and on the other side we are the opposite of what we were. Now this is not sort of the easiest thing to grasp, so if you guys have any comments, any questions, don't be afraid to just leave a comment and I'll help you out. Also, remember the picture. Alright, so now let's talk about how to determine a function's concavity. And so this is actually pretty easy. We just want to find the second derivative and then plug in our value, and whatever the second derivative is will tell us whether we're concave up or concave down. Remember, up is happy, down sad. So in this example, is sine of x concave up or concave down at x equals 2? And don't use your calculator for this one. So you might remember if I sort of poorly graph sine, that it's constantly changing. Here it's concave down, here it's concave up, etc. So I want to find, is it concave up or concave down at x equals 2? So pause your video, unpause when you think you found the answer. Okay, so here, if we want to determine our concavity, we want to find the second derivative and plug in the value. So let's find our second derivative. Y equals sine x is our function. So dy dx equals cosine x. And then d squared y dx squared equals minus sine x. So we have our second derivative. Now let's plug in the value. Minus sine of 2. So you shouldn't actually know this value. This isn't on the unit circle or anything. But we want to think about, well, where is sine positive? Sine is y, so sine is greater than 0 between 0 and pi. If you're confused about this, sort of go back to our third video in the series where I talked about the unit circle in great detail. So since 2 is between 0 and pi, I know that sine is positive, so this is going to be negative. And I'm just asking for what is the concavity. And since d squared y dx squared at x equals 2 is less than 0, we are concave down. We are concave down. We are sad. So that's how you get that. If you guys have questions on that, again, don't hesitate to leave a comment. Alright, so as I talked about earlier in the video, there are things relating to concavity called inflection points. And so what this would mean is at some point we're going from concave down to concave up, or vice versa. Now you can actually find inflection points using the second derivative. So how to do this is we're first going to want to get our second derivative, and next we're going to set the second derivative equal to 0 and solve for x to find possible points of inflection. Now afterwards we need to check if they're actually inflection points. So we want to check our values to the left and right of PPI and find f double prime of x at those values. So we want to plug in values to the left and right of our possible points of inflection into the second derivative. And it's a very similar process to finding critical values and relative extrema using the first derivative test. So if you remember, we put our critical values here, and this is x equals, and we have something less than our CV, something greater than our CV. Here's f prime of x, and if I had opposite signs here, I could say that this critical value was either a relative extreme, a relative max, or relative min. Well, here we can do the same thing for possible points of inflection. We put our PPI here. This is x equals something less than PPI, something greater than PPI, and here's f double prime of x. And if these are opposite, that's saying that we're going from concave up to concave down, which says that this is thus a point of inflection. You know, that's definitionally what a point of inflection is. And so if you do have one, you have to speak derivative, which I talked about in our video relating to the first derivative test. Now this is sort of a lot to take in, so I'll walk you through a quick example. So find all points of inflection for the function y equals x cubed minus 3x squared minus 9x. So first we're going to have to find our second derivative, dy dx. We need to get that first. And then we need to take another derivative to get the second derivative. Now we want to set this equal to 0. and solve for x. And this is a possible point of inflection. So to tell if that's actually an inflection point, we have x equals 1 here, and I need to choose something less than 1, so I'll just choose 0, and here 2, and this is the value of the second derivative up here. So if I plug in 0 to our second derivative, we get -6, and if I plug in 2, I get +6. So we're going from concave down to concave up. So thus, x equals 1 is an inflection point. So now we have to speak derivative. So since d squared y dx squared equals 0 at x equals 1, x equals 1 is a possible point of inflection. Since d squared y dx squared is less than 0 at x equals 0, and d squared y dx squared is greater than 0 at x equals 2, the point 1 comma, and then let me plug that in, 3 minus 6 is -3, minus 9 is -12. Yeah, okay. 1 comma -12 is an inflection point. So to sort of recap, we went through, we got our second derivative, set it equal to 0, solve for x, we got x equals 1. We then did, we made sure that to the left were concave down, and to the right were the opposite of that, concave up. And since we knew x equals 1 is an inflection point, so then we just had to speak derivative and say why x equals 1 was an inflection point. Alright, so you might also know that the second derivative can also be used to test for relative extrema. So to do this, you're going to want to find critical values using the first derivative as normal. So set dy dx equal to 0 and solve for x. Now once you find your critical values, you can use the second derivative test to tell if you have a relative min or max. So here's a quick question. If f of 1 equals, or f double prime of 1 equals -3, and f prime of 1 equals 0, is x equals 1 a relative min or max? So I'll give you a second to think about that. Now, what you should be picturing in your head is our second derivative is negative, so we have down, we're sad. And thus, our point here is a relative max. If we were concave up, we'd have a relative min. So that's sort of how the second derivative test works. So we get our critical values, and then we plug those into the second derivative. Now, a quick note about this. If your second derivative is 0, the second derivative test is inconclusive, and you must use the first derivative test. And as usual, remember to speak derivative. And so how you would do that is you would say the normal, like f prime of x equals 0 at da-da-da, therefore critical value, and then you would say f double prime of x is less than or maybe greater than 0 at da-da-da, therefore da-da-da is a relative min or max. So it's sort of the same thing, but I find the second derivative test is much more convenient in terms of derivative speak and just, sort of doing it. But there are times where you want to use the first derivative test. If my first derivative was, say, e to the x times x cubed over sine ln of x, that's going to be a pain to take another derivative. so I'd want to use the first derivative test. But if f prime of x were equal to, say, x squared, that's a really easy derivative, and I can then use the second derivative test much easier, and I won't have to write out as much in terms of derivative speak. Alright, so let's do a quick example problem. Find all relative extrema for y equals x to the fourth minus 12x cubed plus 40x squared minus 1, and then use the second derivative test for those to determine whether they are relative min or maxes. So pause your video, unpause when you think you found the answer. Okay, so for the first part, finding relative extrema, we want to find values where dy dx equals 0. So first we'll take dy dx, 4x cubed minus 36x squared plus 80x, and now I'll set this equal to 0, and I'll factor out a 4x right away. Whoa, okay, sorry about that. So I'm left with 4x times the quantity, x squared minus 9x plus 20. Alright, so here I can say x equals 0, and now I want to factor this polynomial here. And this is going to factor into x minus 5 and x minus 4. And so my critical values are x equals 5, x equals 4, and x equals 0. Alright, so now, as I said, we want to find whether these are relative extrema, or I'm sorry, relative max or relative mins using the second derivative test. So first I have to find my second derivative, 12x squared minus 72x plus 80. And so I'll plug all these in at x equals 0, at x equals 4, and at x equals 5. So at 0, this is just going to be 80. Now at 4, this is a little more complicated. So at 4, I have to do 4 squared, 16 times 12, minus 72 times, which is going to turn out to be 192, minus 72 times 4, which is 288, plus 80. And so doing this operation, I turn out to get negative 16. And at 5, it's a similar process, 25 times 12, 300, minus 72 times 5, which is 360, plus 80, and this is going to give me 20. So I can say that x equals 0 is a relative min, because we're concave up. Remember, we are happy at x equals 0, so relative min. At x equals 4, we're sad, and so we have a relative max. And at x equals 5, again, we're happy, so we have a relative min. And so let me just sort of give you an example of how to talk derivative. I'll do it for the first one. Since dy dx equals 0 at x equals 0, x equals 0 is a critical value. Since d squared y dx squared is greater than 0 at x equals 0, the point 0, comma, I believe it's 1, negative 1, 0, comma, negative 1 is a relative min. So that's an example of how to speak derivative if you use the second derivative test. Now note that none of these failed. These were all not equal to 0, but if they did fail, we'd have to go back and do the first derivative test. Alright, so that brings me to today's challenge problem. Find all points of inflection for f of x equals x to the fourth minus 6x squared plus 8x minus 13. The solution of this is on our website, learn-ap.com, and the direct link will also be in the description. Guys, if you're looking for other resources to help you learn AP Calc, be sure to check out our resource recommendation video, and that's in the start of the LearnAPCalc playlist. If you guys enjoyed this video, be sure to leave a like. That lets us know that we're helping you guys out and that we should continue to deliver content and do live streams, etc., etc. So if you like this video, please just take the 2 seconds it takes to hit the like button. You can also subscribe for future content. Be sure to like us on Facebook and follow us on Twitter so that you never miss a live stream, and those are from 4 to 5 p.m. Eastern for Calc. Leave a comment if you're still confused about anything in this video, or also any other comments on the video in general. Other than that, I want to thank you guys for watching, and I'll see you in the next video.